There is a narrow corridor where software architecture stops being an internal affair and starts shaping the world outside the screen. In that corridor, two ideas learn to glare at each other across a very long hallway. One whispers about objects that know things and do things. The other whispers about functions that transform the world without touching it. Each has a history, a philosophy, a gallery of famous names, and a trail of consequences in business, law, and politics. The argument is not a campus spat. It is the way most of the modern internet was built, and the way much of tomorrow's infrastructure will either stand up or collapse. Object-oriented programming is the promise that code can be modeled on everyday life. A program becomes a city of small entities called objects, each with identity, state, and behavior. An object is a little shop that remembers its inventory and knows how to sell you something when you ask. This vision was shaped at Xerox PARC by Alan Kay, Adele Goldberg, and Dan Ingalls during the 1970s with Smalltalk. It took off in the 1990s when James Gosling and a Sun Microsystems team created Java, and when Anders Helsberg at Microsoft introduced C#. Enterprises chose these languages to build banking systems, airline reservation platforms, logistics engines, and, later, mobile applications. The pitch was simple. Organize your code like an office of specialists who talk to one another using clearly defined messages. Maintainability would follow. Functional programming is the older, quieter sibling with a very different temperament. Its roots are in mathematical logic and the lambda calculus taught by Alonzo Church at Princeton in the 1930s. The core idea is purity. A function should accept inputs and return outputs without changing hidden state. Haskell was standardized in the 1990s by a committee that included Simon Peyton-Jones and Philip Wadler. Erlang was invented inside Ericsson by Joe Armstrong, Robert Verding, and Mike Williams to keep telephone switches alive even when parts failed. Rich Hickey created Clojure on the Java virtual machine so that a pragmatic, immutable style could live beside the object-oriented giants. Martin Odersky created Scala to blend object orientation with functional constructs and give engineers a smoother path to the future. Each of these languages arrived with the same vow. If state is a wildfire that spreads and is impossible to contain, immutability is the firebreak. What are these things used for? And who actually uses them? Object-oriented systems run the spine of global commerce. Java runs inside the servers at Amazon, Uber, and Netflix. C# and the .NET ecosystem power massive internal systems at Microsoft customers across finance, healthcare, and government. Smalltalk inspired the user interface paradigms that leapt into Apple's DNA and eventually influenced Objective-C and Swift. Functional systems hold different ground. WhatsApp was largely powered by Erlang and handled hundreds of millions of users with a surprisingly small engineering team. Standard Chartered has used Haskell for risk systems. Jane Street, a major quantitative trading firm, is famous for its deep use of OCaml, a functional cousin. Twitter once deployed significant Scala services. Apache Spark, started by Matei Zaharia at the University of California, Berkeley, began life in Scala and became a backbone of large-scale data processing at companies like Microsoft, IBM, and Airbnb. Clojure became a quiet weapon at Nubank in Brazil, one of the largest digital banks in Latin America. The impact is not subtle. When Facebook acquired WhatsApp for $19 billion, it was buying, among other things, the reliability culture of Erlang. When Oracle acquired Sun Microsystems for roughly $7.5 billion, it took stewardship of Java, a language whose reach into enterprise software is measured not in a single line on a revenue statement, but in the budgets of banks, airlines, and insurers that pay to keep their Java estates alive. The cloud platforms at Amazon, Microsoft, and Google sell computation as a utility in data centers spread across continents. Underneath, services written in object-oriented and functional languages coordinate to move money, trade energy, route ambulances, and guide aircraft. If software is the new steel, these paradigms are the blast furnaces. There is a common metaphor engineers use to explain the difference, and it helps. Think of a kitchen. In object orientation, every utensil is an object. A pan remembers it is non-stick. A kettle remembers its temperature. You ask the kettle to boil. You ask the pan to sear. In functional programming, the kitchen is a laboratory. Ingredients go into a function and a dish comes out, but nothing about the lab's apparatus changes in the process. The same inputs will always create the same dish. No memory, no mood. That predictability is priceless when you are splitting the cooking across many stations at once. Concurrency is where the argument left the seminar room and entered the factory floor. When machines acquired many cores, state became the invisible problem. Two parts of a program trying to change the same thing at the same time is like two surgeons working with the same scalpel in the same incision. Object orientation offered locks and monitors and the discipline of careful design. Functional programming offered immutability and message passing. Carl Hewitt's actor model, refined by Erlang and later by the Akka toolkit on the Java virtual machine, said that components should be like postal customers. They send messages and receive messages. No one steals another's mail, and no one opens a shared drawer of variables in the middle of a storm. There is a reason multi-paradigm languages began to colonize the middle ground. Rust, started by Graydon Hoare and developed at Mozilla, and later by a foundation, is not purely functional, but it borrows pattern matching, algebraic data types, and a ruthless approach to memory safety that echoes the functional insistence on explicitness. Modern Java folded in lambdas and streams to encourage a cleaner style. Scala and Kotlin made it normal for everyday engineers to speak both dialects at once. Even C# adopted functional conveniences such as link and immutable records. The market discovered that most of the world is messy, and that any tool that reduces accidental complexity without suffocating the team has value. The money that has flowed through these decisions is measured at national scale. Investment banks priced risk with object-oriented systems and functional systems. E-commerce platforms that ship to hundreds of countries live on Java and Scala. Mobile app economies grew into oceans of revenue because object-oriented frameworks made it feasible for millions of developers to think in terms of screens and controllers and models. Cloud providers rented programming models along with compute and storage. When a senior architect at a retailer chooses between a thread-safe, immutable pipeline and a mutable, stateful object graph, the decision ripples into headcount, downtime, and the balance sheet. Controversy has followed both camps, and it begins, as industry controversies often do, with the law. The long legal battle between Oracle and Google over Java APIs ended in 2021, when the Supreme Court of the United States held that Google's use of declaring code in Android was fair use. It was an object-oriented case about the boundaries of software interfaces and intellectual property. It involved billions of dollars in potential damages and years of uncertainty for mobile developers. The outcome reassured a generation that reusing interfaces is not the same thing as stealing implementation. Functional programming has lived under different legal spotlights. Telecommunications standards and safety certifications meant that Erlang's use in switches had to pass regulatory scrutiny in Europe and elsewhere. The tension between open-source licensing and proprietary deployment has shadowed both traditions, from Richard Stallman's Free Software Foundation on one side to the commercial licensing strategies of large vendors on the other. Financial controversy is quieter but cuts deeper. Vendors that sell object-oriented middleware, application servers, and enterprise support contracts have historically charged significant sums to keep fortune companies within a comfort zone. Licensing for Java distributions, for .NET Enterprise tooling, and for related server products has generated large revenue lines for Oracle, Microsoft, IBM, and others. Functional shops, by contrast, have sometimes been accused of elitism by managers counting salaries and training costs. The perception that a Haskell team is smaller but more specialized can spook hiring committees who fear a single point of failure. Yet the countervailing data points are powerful. The WhatsApp story is not romance. It is a spreadsheet. A small, Erlang-fluent team built a resilient messaging service and sold it for $19 billion. Nubank's Closure Fleet helped a Latin American startup become a bank with tens of millions of customers and a public listing measured in billions. The political dimension is subtler. Governments now legislate on cybersecurity, privacy, and resilience. Paradigms influence how easily a system satisfies a regulator. An immutable audit trail maps neatly to compliance regimes, such as the European General Data Protection Regulation and financial record-keeping in major markets. If your system produces reproducible results from pure functions, auditors smile because they can test and retest. On the other hand, the capacity to evolve a codebase quickly in a crisis, often easier in familiar object-oriented frameworks with vast ecosystems, can satisfy a different political demand for agility. National digital strategies depend, whether they admit it or not, on these choices. Decisions made at Park, Ericsson, and in academic workshops in the 1980s ripple into cabinet rooms today. The technical controversies are the most passionate because they are very personal. Object-oriented engineers argue that modeling the world as objects meshes with human cognition. They cite Barbara Liskow's substitution principle from the Massachusetts Institute of Technology, the Gang of Four Design Patterns catalog by Eric Gamma, Richard Helm, Ralph Johnson, and John Vlissides, and a universe of frameworks that have proven their value in the field. Critics respond that inheritance chains become vines that choke a codebase, and that mutable state invites the worst kind of bugs, the ones that appear only under load at 2 a.m. Functional engineers advocate purity, types that rule out entire classes of errors, and explicit effects captured in constructs like monads. Their critics complain about opacity, about error messages that read like homework from a graduate seminar, and about the friction of rewriting a problem in a purely functional skeleton when a pragmatic, mutable data structure would do. The arguments are not academic bluster. They decide whether a social network stays online during a traffic surge or whether a hospital scheduling system drops appointments on a Monday. Deeper technical ideas deserve a careful walk. Immutability reduces the surface area where race conditions can breed. If data never changes, you can copy it freely and spread the computation across threads or machines. Persistent data structures, popularized by computer scientists like Chris Okazaki, allow efficient updates that share structure under the hood. Pure functions compose like Lego bricks because each is a self-contained promise. This encourages designs where pipelines of transformations can be reasoned about, tested thoroughly, and parallelized. The cost is that reality is not pure. Reading a sensor, charging a credit card, and writing to a database are side effects that must be managed. Functional languages use types to corral these effects and tell the truth about where impurity lives. Object orientation's deeper ideas revolve around boundaries and contracts. Encapsulation protects invariance. A class can guarantee that its internal state never violates rules, something like a vault that never opens its door while the combination lock is turning. Polymorphism allows many kinds of objects to respond to the same message, which is a gift when designing large systems where the exact kinds are not known in advance. Composition over inheritance is a hard-won lesson that says large behaviors should be built by hooking smaller behaviors together, not by climbing precarious family trees. The cost is vigilance. Shared mutable state is powerful and dangerous. It can be managed, but the skill is not evenly distributed, and even skilled teams are fallible. Related technologies fit into this story, like minor characters whose choices change the plot. The actor model in Erlang and Akka is a functional response to coordination at scale. It complements object-oriented designs by moving shared state behind mailboxes. Apache Kafka, created at LinkedIn, is a stream backbone that makes immutability tangible by treating events as an append-only log. CQRS and event sourcing in enterprise architecture borrow from functional thinking by privileging the truth of an event history over an always mutable snapshot. On the other side, object relational mappers in Java and C# gave businesses the courage to put complex state in databases without writing every query by hand. Frameworks like Spring from Pivotal and ASP.NET from Microsoft proved that object-oriented scaffolding could scale across thousands of developers with repeatable patterns. There are facts that sound like rumors until you check the citations. Ericsson built Erlang because telephone switches had to achieve 5 nines of availability, which means minutes of downtime per year, not hours. That culture shaped an entire branch of functional thinking around supervision trees and crash-only software, where failure is expected and contained rather than denied. The Haskell community's work on strong type systems influenced production-grade compilers and provers that caught errors before deployment. The Smalltalk world left fingerprints on graphical user interfaces that are now so ordinary they are invisible. Sun's motto for Java, "Write once, run anywhere," was not marketing poetry. It became a portable, virtual machine reality that let large firms move workloads across hardware vendors and data centers with a degree of confidence unusual for the 1990s. Organizations known and less known carry these ideas into the present. Amazon's retail core has long relied on Java. Netflix open-sourced libraries in the Java ecosystem that many other companies rely on. Spotify has used a mix including Java, Scala, and Python. Nubank's closure shows that a bank can be born in a functional mindset without losing speed. Klarna in Sweden used Erlang in its payment stack. Basho, the company behind the React database, used Erlang to craft a highly available key-value store. The Academy for Programming at the University of Glasgow remains a beacon in Haskell research. The University of Kent and the University of Edinburgh shaped generations of functional programmers. Microsoft Research funded explorations that flowed into F#, another blend of functional and object-oriented ideas. Broader impact is always the question worth asking. What have these paradigms done to humans, to the Earth, to our experience of reality? Object orientation made it easier to describe user interfaces, to teach programming to millions, and to coordinate large teams across cubicles and continents. That accessibility helped software eat more of the world, with all the carbon and energy implications of clouds and data centers that followed. Functional programming helped the industry build reliable distributed systems, tightening the bolts on the platforms that now feed recommendations, plan logistics, and balance energy grids. The predictability of immutable, parallel pipelines is part of why renewable energy forecasting and climate modeling can run at the scale they do. When a hospital records an immutable stream of events and later reconstructs a patient's history, a life can be saved because there is a single source of truth rather than a collection of silent contradictions. There is also the human texture. Teams that choose a paradigm choose a culture. Object-oriented teams often value domain-driven design, a concept promoted by Eric Evans, where the language of the business is encoded in classes and services. Functional teams often value laws and proofs, where the type system is a guardian and the code is a conversation with mathematics. Both are forms of care. Both can nurture or alienate. The real danger is not choosing one or the other. It is lying to oneself about the costs. So what should be built when the stakes are sky high? A global messaging platform with constant churn and relentless concurrency might fall in love with Erlang-style actors and immutable data. A large enterprise rewriting a legacy payments hub might depend on mature Java ecosystems with a carefully constrained functional style tucked inside. A safety-critical component in a browser engine might be written in Rust with functional patterns and strict ownership to avoid memory mistakes that become security vulnerabilities. A high-frequency trading desk might stick with OCaml or Haskell, where the compiler is a partner that slaps hands before a trade goes wrong. The clash is real, but it is not a duel to the death. It is an argument between two successful families at the same table. The most interesting languages today are bilingual. Rust speaks low-level systems and high-level algebraic types. Scala can be imperative or pure. Kotlin gives Android developers safer ways to write what used to be worrisome Java. Modern Java and C# have gained lambdas, pattern matching, and immutable collections because their users demanded less friction with modern hardware realities. Even JavaScript, which began as a hurried scripting language, has learned functional idioms at industrial scale at companies like Meta and Google. The industry has learned to mix metaphors with care, build services as objects with clear interfaces. Inside those services, treat data as immutable as long as possible. Use message queues and logs to move events, rather than shared mutable state. Let the compiler help where it can. Put the unpredictable, side effect-laden code at the edges. Keep the core pure and testable. Accept that most businesses will not hire only mathematicians or only pattern catalog devotees. Teach both. It is not compromise, it is engineering. There is a final fact worth holding close. Good software is not just circuitry and syntax. It is a social contract. Object orientation and functional programming are two ways to keep promises to the future. One way says that a set of collaborating experts will keep their stories straight. The other says that the same inputs will always produce the same outputs, and that lies will be caught at compile time. When those promises are kept, planes land, hospitals function, and money moves. When those promises are broken, headlines are written, and trust is lost. In the long hallway, the glare has softened. The two traditions still argue, but they now listen. They have to. The systems they support are older than some of the engineers who maintain them. The planet that depends on those systems is impatient. The next decade will not reward purity for its own sake. It will reward the teams who pick the right ideas at the right scale, who can articulate the legal risks, who understand the balance sheet implications, who can satisfy regulators, and who can explain to a new hire why this kitchen looks like both a home and a lab. That is not a truce. It is a discipline. It is how software grows up.